Hi, and welcome back to Historical Geology, and today I want to finish up PowerPoint for Chapter 4. And these last couple of parts deal with carbon-14 dating and tree ring, or dendrochronology type of dating. Now for carbon-14 is an isotope of carbon that's continuously being made in the upper atmosphere. And the way it works is we have cosmic rays or cosmic radiation that comes down in the form of protons or electrons or neutrons, and neutrons will essentially bump a proton out of the nucleus of nitrogen-14, because remember, 78% of our atmosphere is nitrogen, so we have lots of this nitrogen. And so if a neutron bumps a proton out of the nucleus of nitrogen-14, what happens is we still have the same atomic mass, but now we've converted a proton to a neutron. So now that means the atomic number must decrease by 1. So remember, the atomic number of nitrogen is 7, carbon has 6, right? So we lost a proton, so now this becomes carbon-6, but we didn't change the weight because we just replaced that proton with a neutron. So anyways, that's always happening. It's a continuous supply in the atmosphere. And so carbon is a component of carbon dioxide. As long as the plant is alive, it's going to be absorbing carbon that has some carbon-14, right? Most of it's going to be carbon-12, maybe a little bit carbon-13, but most of it is 12, but it will get some of that 14. And as long as it's alive, it's getting a constant supply. Every time it does photosynthesis, it's getting that supply of carbon-14. So in other words, the decay of carbon-14 really cannot be measured until the animal dies, right? Animals who eat the plants, well, they're getting their constant supply, right? So as long as the organism is alive, because it's continuously being formed at a relatively constant rate in the upper atmosphere, every living thing is getting carbon-14. As soon as the organism dies, then the decay process begins. The atomic clock closes, and we begin to accumulate nitrogen-14, because carbon-14 will decay by beta decay back to nitrogen-14. And so that's where the atomic clock begins. So, and then that's how carbon dating works. One important thing about carbon dating, the half-life of carbon-14 is about 5,730 years. And so you really can't date anything older than about maybe 55 to 70,000 years. Some textbooks say 70,000 years, but really it breaks down anything much older than about 55,000 years. So it's really for younger deposits, and like coal or charcoal or bones or something, but something that must have been around in the last 50,000 years or so. So in other words, you cannot use carbon-14 dating on dinosaur bones, because dinosaurs lived millions of years ago, more than 65 million years ago, and carbon-14 doesn't work on anything that old. So it only works on something that's about maybe 50,000 years, 55,000 years and younger. Now the other method of dating is tree ring dating. And the way tree ring dating works is that each tree ring represents 1 year. So you can literally take a living tree and count basically the rings and figure out how old that tree is. And so by doing that, you can take a living tree and especially some of these like old redwood trees that live for several hundred years, you can count back the tree rings. And one thing you would notice is in these little images, patterns of tree ring growth. There might be really wet years, or maybe where the rings are really close together might be a dry period. And so think of these as like fingerprints or to a climate or a change in the weather during this period of time. In this case, this tree, we're looking back about more than 200 years in this case. And let's say we were looking at an old adobe structure out in the American Southwest, and we want to figure out when the people made this adobe, and then you look at the timbers. So maybe they chopped a tree down, and so if we look at the tree rings in the timber, we see that they match in this region from about 1800 to 1850. So we can get a numerical age using this cross dating or tree ring dating. Another word we have for tree ring dating is called dendrochronology, and it's the same idea here. Here we have a tree that's going to about year 1990, 2000 here, and we can date this living tree going back to about maybe 600 years. So it'd be a tree that's lived over 600 years here. But then we can match it to a tree that probably died about maybe 500 years ago, but then it can be traced back even farther to maybe the year 1100 or so here. And then we find another tree that we can use this to date even farther. So again, we can go back and accurately get ages, in this case over in the year 800, which is over 1200 years from today, from the year 2000. And this technique of dendrochronology can go back to about 14,000 years.
The next thing I want to cover here is look at the applications of relative dating. And again, we're looking at, the relative dating principles of original horizontality, superposition, lateral continuity. In fact, we have them here in the textbook. You can see we had position, final succession, lateral continuity, cross-cutting relationships. So we want to apply all those to these relative ages puzzles. I call them puzzles, so we try to figure out their ages. So here's some examples from your book, from the reading assignments we have for this week. And in this picture here, this is some quarry in Germany, and we're looking at basically 3-4 things going on here, right? So there's this metamorphic gneiss, which is probably the oldest thing here. And then we have this igneous intrusion, which is an igneous dike. And there's a note here that there's some burning or baking along the edges of the dike, burning the gneiss, in other words, which means that this igneous intrusion was hot and the gneiss was cold, so there's this contact metamorphic zone there, which tells us the igneous dike came after or is younger than the gneiss. Again, the other principle we use is a dike here clearly cross-cuts or cuts across the gneiss. So remember, the cross-cutting unit, which is a dike, will be younger than the unit being cut, right? So the oldest thing appears to be the gneiss here, the metamorphic gneiss. Then we have the igneous dike with the hornfels or the contact metamorphic zone along the edges. And then the youngest thing is probably the sandstone, which just sits on top, and we'll probably use superposition for our principle there. But note that there's another event here that we really don't see because it's a time gap. You're missing. So the rocks that used to be above the metamorphic rocks here, the gneiss, or even the igneous rock here, the dike, have been eroded away and made an old paleo surface where the sand came to rest on top, right? So whenever you have an unconformity, so it's a gap in time, in this particular case, we have sedimentary rock or sediments on top of crystalline basement. Remember, the crystalline basement is either some plutonic igneous rock or some metamorphic rock. In this case, it's a gneiss, metamorphic gneiss. So we have to call this a nonconformity. So if we were to establish or write out the sequence of events, the oldest, or number one at the bottom, would be gneiss. We always go from bottom to oldest at the bottom to youngest at top. So you'd put 1 for oldest rock, being the gneiss. The second one would be the igneous dike, 2. The third event would be the nonconformity, which is that erosion event that stripped away the rocks that were there before to make a new surface. And 4, the youngest thing, would be the sandstone. So 1, 2, 3 for the nonconformity, and 4 is the sandstone. So that's kind of our relative time dating sequence for that example there. And then your book also has example 2, and I like this one here because it kind of got a valley here or some farm field with some geology going on at depth, right? So in this case, looks like we have a fault here. This letter A is a fault. We have a couple of igneous intrusions. So this kind of cross pattern here is probably like a granite or some sort of plutonic rock. The little V's, or sometimes they're check marks, indicate like a basaltic dike or some sort of volcanic intrusion or shallow intrusion. In this case, a dike or a sill, right? So in this case, we're going to use our principles of superposition and cross-cutting relations to kind of help us out here. So, for starters, we say superposition, the oldest unit's always on the bottom, but there's a clue here. The clue here is this purple little zone here that occurs both in the granitic rock H and in this basaltic dike G. And what that purple zone means, that's that contact metamorphic zone, which means it's a bake zone, it's a burn zone. So this H must be younger than these units it's burning, right? Because these units were there and this letter H came in after these units were already there. So this is an example where the oldest unit is not at the bottom because this is an intrusion, an igneous intrusion, right? So that means that it must be these sedimentary rocks. So whenever you see a brick pattern, that indicates a limestone. This angular kind of sedimentary rock, that looks like a breccia, some sort of breccia. If it were round, it'd be a conglomerate, right? That's usually a sandstone, the little sandy, grainy pattern there. Shale would be this. Shale or mudstone would be something. This is kind of a shale or mudstone as well. And then this one doesn't have, oh, there's more bricks. That's another limestone right there. So for this example, the oldest thing we can say here would probably be letter F, which is this older limestone. And we just use this principle of superposition. So it'd be F, E, D, C, B, and J, right? So that would be our oldest rock is F, and then we go up to J here. And then the next thing that's happening is we can't tell whether the fault A or the intrusion H is older because they don't intersect. So then what would be next would be either the intrusion of this granitic rock H, because it's burning, there's this contact metamorphic or bake zone here, it's burning these sedimentary rocks. So that's coming after this sequence F through J, and then it's probably letter A would be the fault. So, or it could be A and then H, so we really can't tell. In fact, your book down here makes that distinction. It says you got the oldest rocks here, F, E, D, C, B, and J, and then it could be H or A, right? And so that would be our sequence going on there. Then it's clear that G is younger than both the fault because there's some contact metamorphic zone or bake zone there, and you're baking the granitic rock here. So G would have to come after A or H, right? So we'd go F through J, then H, A, G, right? Then we have this surface erosion here, right? And note that this erosion is parallel to the strata, right? So letter I would be a disconformity, another erosion event, and we call those disconformities. And so what are they? Yeah, they do have I as the youngest unit here, right? Yeah, and then G would be the dike, right? And so one thing that they don't give you here, and they want you to read on about these disconformities, right? And so the disconformities would be the time gaps, right? And so we do talk about those. Your book will talk these unconformities, missing time gaps, right? So if we kind of look here real quick, right? So there's a major disconformity here in the Grand Canyon, right? Between the Proterozoic rocks and Phanerozoic rocks, right? So, and this is clearly some angular unconformity, right? And so let's see if I can find yeah, so here's the Temple Butte Formation and the Mauve Limestone. So there's usually a disconformity between these units here. Yeah, disconformity. They do have it right in there. I know that from my studying of the Grand Canyon. And you can kind of take a look at some of these images they have here. In fact, this is some disconformity back east, some angular unconformities here. So you can take a look at those. But for our purposes, I wanted just to kind of go over that diagram. Also, in our lab for this week, we're doing these for our lab. We're doing these relative time puzzles here. So I have them right here. It's a pre-lab, and when you click on this will come up. Let's see if I can center this thing in here. There it goes. The way this is going to work is kind of the same idea. You're gonna look at this relative time diagram, and you always want to put the oldest units on the bottom. For example, here looks like we have a stack of sedimentary rocks here that are clearly tilted. So in this case, we're using the principle of original horizontality. And then there's a second stack, letter G through D, that's also tilted. Actually, this goes all the way to A. And then there's this intrusion of letter C in here. This is some sort of igneous rock. So again, to help you with the symbols, I did include this relative ages diagram to show whether they're sedimentary rock, igneous. This one even has those contact metamorphic rocks. So you can see that this is the bake zone or burn zone along the margins of this intrusion letter C. And so the way you want to do this, you want to grab the oldest unit, in this case probably M, and put it in the little box there. And keep grabbing those, and don't forget about this unconformity right here. That's going to go in here as well. So there should be a space for all these letters, right? So once you complete a diagram, you can check your answer. So you're going to get it right one way or the other, right? But I don't think it's going to save it for you. So you're going to have to take like a screenshot of it or something and save it onto your computer, onto your phone, and then later on upload it with the assignment. So that's one caveat with this exercise. But then you'll see that there's some questions, right? So make sure you answer the questions, and you can, when you submit this, you could either submit it as a text file or a document, right? But you're going to have to answer the questions for relative diagram 1, which are questions 1 through 4. You can see I have another relative time diagram over here, number 2, and you'll have questions 5 through 9 down here. So again, you're going to drag the oldest. In fact, this one's probably, letter C is probably the oldest here, right? And there's some sort of folding, some bake zones, some intrusions, some sort of unconformity there, right? So your job is to kind of figure those out. And again, the nice thing about this, you'll be able to get the right answer by doing the check. So you can do this multiple times, right? All right, so that's it for the geologic puzzles there. Let's go back and look Geologic Time Lab, which I have here. And so on this one, I think, I have a video. It's also download the lab. It's a fillable PDF. Download the lab, watch my video, and then you'll see that it's going to ask you to use pennies and nickels, right? You probably don't have a bunch of pennies and nickels lying around. So I went ahead and did that experiment for you, and I have the data here. So use these data when you do the absolute time part of this lab there. All right, that's it for this week. See you next time.